morning everybody, hope you're all healthy and safe. So we are going to continue with our section 6.4 on projections. So as I had mentioned earlier, in this lecture, in the previous lecture we had discussed, or we had studied what is a projection, and we studied few properties related to the projections. So in this lecture we shall be going on to another level, that is, we are going to discuss about the concept of ortho projections. Okay, so what is meant by an ortho projection? So ortho projections is it is actually a projection itself in a Hilbert space is said to be an ortho projection if P equal to P star, that is, it must be symmetric. Okay, if the projection that we are considering is symmetric, then we can say that that particular projection is a ortho projection. So you can say ortho projection is also actually a property of the projection. Okay, if the projection becomes symmetric, then we call that type of projections to be ortho projections. That is, inner product P of x y is equal to inner product x P of y for all x and y in the Hilbert space H. So just like we had done in projections, here also we shall be discussing few properties of ortho projections. The first one is, if P is an ortho projection, then image of P is orthogonal to kernel of P. Okay, so we need to show that image of P and kernel of P are orthogonal to one another. So let's see how we can do that. So for that, first of all, just recall the properties of projections. We have seen that in projections, image of P or image of Q, we need to show that image of P is orthogonal to kernel of P, right? So I can write this as image of P should be orthogonal to image of Q or image of I minus P. This was a property of the projection, right? So instead of proving this, we will be proving this, that is, image of P and image of I minus P are orthogonal. So I'm going to choose two elements. Let P of x be an element of image of P, and say I minus P of y belong to image of I minus P. Okay, now we need to show that they are orthogonal. So for that we have to determine the inner product. So inner product P of x comma I minus P of y. So this can be written as inner product x into P of I minus P of y. Why? Because P is a projection. This is equal to inner product x P minus P minus P square acting on y, that is P of y minus P square of y. Now what is P square? P square is again P. Why? Because P is an ortho projection, and every ortho projection is a projection, right? So this is nothing but inner product x comma 0, and we get this is equal to 0. So if I take any element from image of P and image of Q, the inner product is always coming out to be 0. So I can say that image of P is orthogonal to image of Q. That implies image of P is orthogonal to the kernel of P. Then this is true in case of the projection, not a projection, sorry, ortho projection. Okay, this property is satisfied for ortho projection. So that was a simple property. Now let's move on to the next one, that is, every ortho projection P satisfies 0 less than equal to P less than equal to I. Okay, that is, every ortho projection will always lie between 0 and I, the identity operator. So let's see how we can prove this. Sorry. So we need to show 0 is less than equal to P less than equal to I. So first let's see what is inner product P of x. this can be written as inner product p square xx. Why p is equal to p square? Because p is an ortho projection. So I can write this as p of x. Now since p is an ortho projection, this is same as inner product p of x. This is nothing but norm of p of x square, and norm is always greater than 0. So I get p is actually a non-negative operator. Therefore, p is greater than or equal to 0. Okay. Now, in a similar manner, we need to show that p is less than or equal to I. So, how can we do that? To show p less than or equal to I, it is enough to show that I minus p is greater than or equal to 0. That is, I minus p is a non-negative operator. It is enough to show this. Okay, right? So let's take I minus p of x comma x. This comes from the definition of non-negative operator. Now this is nothing but inner product x minus p of x comma x. This is equal to inner product x comma x minus inner product p of x comma x. Now this p of x, this inner product x comma x is nothing but norm of x square, right? And inner product p of x comma x, just now we have seen that it is nothing but norm of p of x square. Now we just need to show that both these terms are greater than 0, but their difference, it is possible that it can be less than 0, but this is actually greater than 0. We shall show that. How can we show? There is a result, that is, we have norm x square is equal to norm px square plus norm of I minus p of x square. Okay, so from this I can get norm of x square minus norm of px square is nothing but norm of I minus px square, which is again greater than 0, being the norm. Okay, so let me prove this. Okay, how can we do that? Let me take norm px square plus norm I minus px square. So using the definition of inner product, this is nothing but p of x comma p of x plus inner product I minus p of x comma I minus p of x. So this is nothing but x comma p square x plus inner product, I am just writing this, expanding this, this is x minus p of x, x minus p of x, p square is p, so this is x p of x plus, let me just expand this, this is x comma x, then I have minus inner product x comma px, then this term, that is minus inner product px comma x minus minus plus inner product px comma px. Okay, now except this term, all other terms will get cancelled. Why? See, x px will get cancelled over here, and here we have minus pxx plus inner product pxx. So since p is an ortho projection, I can take this p to this side, so this becomes p square and p square is p, so I get x px. So this term and this term will also get cancelled. Both these terms will be same. Okay, so what we can say, this is equal to nothing but inner product xx, that is nothing but norm of x square. So we have this result. So with the help of this result, I get that norm x square minus norm px square is equal to norm of I minus p of x square. Therefore inner product I minus p of x is nothing but norm of I minus p of x square, which is greater than or equal to 0. This implies I minus p is greater than or equal to 0, and hence e is less than or equal to I. So this is what we had to prove. So for every ortho projection, the property that we have done just now is that corresponding to every ortho projection, we'll have the inequality which states that 0 is less than or equal to p less than or equal to I. Okay, so now let's move on to the next property. The next property, it gives us an idea about the sum of two projections. If we are considering two ortho projections, okay, and let ei be the image of pi, okay, so e1 will be image of p1, e2 will be image of p2, where p1 and p2 are through ortho projections. Now if p1 p2 equal to 0, then so is p2 p1. So whenever p1 p2 is 0, then p2 p1 is also 0. Also we have another concept or another result, that is that this e1 and e2, that is the image of both these projections, they will be orthogonal, and also p1 plus p2 is an ortho projection onto e1 plus e1 direct sum e2. Okay, so what are the things that we have to prove? First thing, if p1 and p2 is 0, then so is p2 p1. We need to show that e1 is orthogonal to e2, and we need to show p1 plus p2 is an ortho projection. So let us now move on to the proof of this property of the ortho projection. So first of all, e1 is nothing but image of p1, and e2 is image of p2. Or now p1 and p2 are ortho projections, so they are actually acting on the Hilbert space h to h, right? So we can write this image of p1 p2 as p1 of h also, and p2 of h, right? Image of p1 and p2. Okay, so first let us prove that p1 p2, if suppose that p1 p2 equal to 0, we need to prove that p2 p1 is equal to 0. Now let's see how we are going to do that. Let us first find what is inner product p2 p1 x y. Okay, since p1 p2 are ortho projections, I can write this as p1 of x, p2 of y, and this is again p1 is again an ortho projection, so this is p1 p2 of y. So p2 p1 acting on x comma y, inner product of p2 p1 x comma y is nothing but inner product x comma p1 p2 of y. So from this what do I get? I get that p2 p1 is nothing but p1 p2 star, right? Now p1 p2 is 0, so p1 p2 star will also be 0. p1 p2 is a 0 operator, so p1 p2 star is also 0. So from this what do I get? p2 p1 is 0. Okay, so we have proved that p2 p1 is 0 whenever p1 into p2 is 0. Now next, so first thing we have proved. Now next what do we need to prove? Next, to prove e1 is orthogonal to e2, or I can say p1 of h is orthogonal to p2 of h. Right, so let us take the inner product. What is inner product? p1 of h, p2 of h. Now this can be written as inner product h comma p1 p2 of hy, because p1 is an ortho projection. p1 p2 is nothing but 0. So this is 0. Therefore E1 is orthogonal to E2. Alright, now next what do we need to prove? So everything is a simple proof. We need to show that P1 plus P2 is an ortho projection, right? This is what we have to prove. Okay, so first we need to show whether P1 and P1 plus P2 is a projection or not, and it should be symmetric, then it becomes an ortho projection. So let us take P1 plus P2 whole square. This is nothing but P1 square plus 2 P1 P2 plus P2 square. P1 square is P1 itself because it is an ortho projection. P1 P2 is 0 plus P2 square is P2. So this is nothing but P1 plus P2. Therefore P1 plus P2 is a projection. So now we need to show whether it is symmetric, right? Now, so for that I'll consider P1 plus P2 of X comma Y in a product. Now this is P1 of X plus P2 of X comma Y. By the property of inner product, this is P1 of X Y plus inner product P2 of X comma Y. Now P1 and P2 are ortho projections, so I can write this as inner product X comma P1Y plus inner product X comma P2 of Y. So again by linearity of inner product, I get this as P1 of Y plus P2 of Y. So this is nothing but inner product X comma P1 plus P2 of Y. Therefore P1 plus P2 is symmetric, and hence I can say that P1 plus P2 is an ortho projection. So this was our third property related to ortho projections. So that is P1 P2 is equal to 0 implies P2 P1 is also 0, and E1 and E2, which are the sum, which are actually the images of the particular projections, ortho projections, they are actually orthogonal. And finally P1 plus P2 is also an ortho projection. So there are a few more properties of ortho projection which we shall be discussing in the next lecture. So that's it for today's session. Thank you. Stay safe and stay healthy.